think about the scientific revolution, some great people might come to your mind. Sir Isaac Newton, Galileo Galilei, Johannes Kepler, or Nicholas Copernicus. However, many scientists and mathematicians who have made great contributions have been swept under the rug in the frenzy of scientific discoveries during the revolution. One of these people is someone who you might have never heard about, yet his works are still very impressive even by today's standards. Greetings everyone, I'm your host Seichu, and here's the story of Pierre de Fermat. Pierre de Fermat worked as a lawyer, but he had always been fascinated with math, and when he came home from work, he would always work on math. He didn't publish any of his work, but his work got recognized only because he showed his work to other mathematicians who were impressed with him. Fermat and René Descartes were the leading mathematicians of the 17th century, and both Fermat and Descartes discovered the fundamental properties of analytical geometry independently of one another. Fermat was born August 17, 1601 in Beaumont-de-le-Mont, France. He was born to a wealthy father and a noble mother. However, his mother died while he was young. As a child, he was fascinated with math, as mathematicians at the time, such as Euclid, Viet, Apollonius, and Denas as hobbies. More specifically, he was interested in working with curves. Fermat studied law, most likely in Toulouse. He might have also studied at Bordeaux when he moved there. He then received his bachelor's degree in civil law at the University of Orléans. Fermat is most famous for his works in number theory, his work on curves, Fermat's principle, and Fermat's last theorem. Now, it is important to note that those were nowhere near all the discoveries he has made. He has also contributed in a lot in early calculus, analytical geometry, probability theory, and so on. However, only the first three will be discussed later. As I said before, Fermat has been obsessed with curves as a child. This persisted after he reached adulthood, as he would continue to work on curves, and it became one of his most famous works. He also discovered Fermat's principle of least time, also known as Fermat's principle, or principle of least time for short. To understand it, think about it like this. When you are swimming and you're trying to see the pool floor below the water, it seems distorted. Fermat thought that perhaps light doesn't always take the shortest path, but instead it takes the path of least time. This is because light is traveling through different media. In this case, it will be air and water. Water is denser than air, so light will be slower on water than if it was traveling through air. This also has real-life applications. Let's say you are a lifeguard at a beach, and you see someone drowning. What path should you take? Ideally, the path should be short, while at the same time, it should also minimize the distance you travel in the water, as drowning on sand will almost always be better. In this situation, you should take the path that is in the middle of the shortest path and the path that minimizes the distance in the water if you want to reach the drowning person the quickest. Fermat was also known for his work in number theory. Some of his work includes Fermat's little theorem, which states that if p is prime and a is any whole number, a to the power of p minus a will be divisible by p. For example, if a is 12 and p is 7, then 12 to the power of 7 minus 12 would be 35,831,796, which is indeed divisible by 7. Another example is the 4k plus 1 and 4k minus 1 primes. 4k plus 1 primes are any prime number that are 1 more than a multiple of 4, for example 5 or 97. Fermat states that all 4k plus 1 primes are the sum of exactly one pair of square numbers. For example, 5 can be written as 1 squared plus 2 squared, and 97 can be written as 9 squared plus 4 squared, and they can only be sums of those two squares. Meanwhile, 4k minus 1 primes are any prime number that is exactly 1 less than a multiple of 4. For example, 379. Fermat states that 4k minus 1 primes cannot be decomposed into any two square numbers no matter how hard you try. Don't ask me how he thought about this or how this is useful in any way, because I honestly do not know. He also stated 2 to the 2 to the n plus 1, assuming n is a positive integer, the sum must be a prime number. For example, 2 to the 2 to the 1 plus 1 equals 5. 2 to the 2 to the 2 plus 1 equals 17. 2 to the 2 to the 3 plus 1 equals 257. And 2 to the 2 to the 4 plus 1 equals 65,537. All of which are prime numbers. These will later become known as the Fermat primes. However, this is quickly disproven as 2 to the 2 to the 5 plus 1 equals 4,294,967,297, which is in fact not a prime. What is the divisible by, you might ask? 641 and 6,704,417. Nowadays, numbers in the sequence past 65,537 are known as Fermat numbers, as 65,537 is the largest known Fermat prime. With this knowledge, we can also construct the hexameria, pentakilia, pentatetrahedronta heptagon, also known as the 65,537 gon, which is the largest known prime-sided regular polygon that can be constructed using a compass and an unmarked straight edge. Honestly, at this point, just use the compass to draw a circle. Something that he was very famous for was Fermat's last theorem, which states that for the equation a to the n plus b to the n equals c to the n, if a and b and c are all positive integers and n is number greater than 2, the equation cannot be solved. We can put this into practice as 1 to the 1 plus 1 to the 1 equals 2 to the 1. Pretty obvious so far. And for a squared plus b squared equals c squared, that sure sounds familiar. It's a Pythagorean theorem. Plug in the Pythagorean triples, 3 squared plus 4 squared equals 5 squared, and there you go. This equation is solvable when n equals 2. In fact, there are an infinite amount of solutions. However, things get a lot more complicated when we get to n equals 3, n equals 4, n equals 5, and so on. In 1637, Fermat wrote in Latin in the margin of his copy of the book Arithmetica by the Alphaeus of Alexandria, a note that roughly translates to, "I have a truly marvelous proof which this margin is too narrow to contain." He never published the proof, and after his death, his son Clément Samuel published the 1670 edition of Arithmetica, which included his father's notes. Fermat claimed to have a proof for a lot of stuff, but every time he wrote it in the margin, he would always have an excuse following it, such as, "I have a proof for blank, but I have to feed my cat." The book was filled with these notes, and nearly all of his claims he wrote in the margin was proven by other mathematicians, except for one, which was Fermat's last theorem, which baffled mathematicians for centuries, and many people would take on the challenge, but every attempt they would make a flaw, and then the theorem would remain neither proven or disproven. This continued as no one could come up with a proof for his last theorem until 1994. By then, mathematicians discovered that it could prove the Taniyama-Shimura conjecture, which I would not be getting into today. You can also prove Fermat's last theorem. Then comes Andrew Wiles, a Princeton professor who was obsessed with Fermat's last theorem since he was 10 years old. And he worked on the Taniyama conjecture for 7 years until he got it, and with the help of Richard Taylor, which was one of his former students, he published the proof, and so the 350-year conundrum was finally over. His biggest controversy was that he had a habit of not providing proofs for his claims. This can be problematic, as seen with the Fermat primes, and especially problematic as if he had a proof for his last theorem, he wouldn't have spent 350 years on it. And a common misconception was that his last theorem was the last claim he had written down, and he had died before he published the proof, but that's false. He wrote the theorem sometime in 1637. He died in 1665, so if the myth was true, he had about 28 years to work on the proof, but he never published it. The truth is, while all of his other claims were proven to be true or false relatively quickly, his last theorem was the last theorem to be proven true or false. A lot of other people also believe that because Andrew Wiles' proof in 1994 was so complex and used many tools that didn't exist just 100 years ago, there was no way Fermat could have thought of a proof more than 350 years ago, and perhaps he never had a proof at all. However, because all of his other claims seem to be proven quite easily, it doesn't seem likely that he didn't have a proof for his last theorem. Instead, what has most likely happened was he thought he had a proof, but because he didn't publish it, he could have made a mistake somewhere in it. This is further backed up by the numerous mathematicians who had attempted this theorem just to find out that they had a mistake somewhere in the proof, which probably would have happened to Fermat. However, it is still important to note that mathematics was not as rigorous in the 17th century than it is now, and especially when combined with the fact that Fermat was a lawyer and not a professional mathematician. Another challenge he had was, although he had developed analytical geometry independently of René Descartes, he barely received any credit for it, and nowadays Descartes was largely credited for discovering analytical geometry. It is sort of similar on how Gottfried Leibniz developed calculus independently of Newton, while Newton was getting all of the credit. Fermat's work in number theory, along with other works, such as his contribution to probability theory, would have a lasting impact on mathematics and science, as along with Blaise Pascal, he became the co-founder of probability theory. Probability theory would later evolve into stuff like quantum mechanics. Fermat's principle would also be useful to solve the problem of the fastest ascent. His contributions to analytical geometry bridged the gap between algebra and geometry, and I can go on and on about all the impact he had, but I'll have to stop there. So in essence, although Pierre de Fermat wasn't a professional mathematician, perhaps that is what made him unique. Because most of his claims were published after his death, it left mysteries that would be unsolved for centuries. Even if he was a lawyer, his work in mathematics is still awe-inspiring, especially his work in number theory, curves, and optics, which revolutionized their respective fields. The work that other mathematicians contributed on top of his is also very impressive, especially that of Andrew Wiles, which he spent 7 years working on. This story shows that you don't need to take the conventional path if you want to make a lasting impact. Now, I just want to say thank you for watching my documentary, and have a great rest of your day.